Welcome to today's lesson on differentiating natural, exponential and logarithmic functions. By the end of today's lesson, you should be able to differentiate these types of functions and hopefully understand why they're differentiated in this way. We're going to start by looking at graphing the n derivative command on your GDCs. So in the same way that we can find the derivative of a point, we can find the derivative of a graph. I'm going to do sine x here because we did that yesterday and we're comfortable with it. So you enter it in as you can see it, and there I have the derivative of sine x, which is the graph of cos x. And just for reference's sake, I'll show you the graph of sine x, and we can confirm that this is actually sine x, and the blue line is its derivative, cos x. Let's look at the n derivative command and compare a graph of e to the power x with its derivative. We can see that the derivative is the same as the original function. Let's have a look at a little bit more detail about why that works. So this is the equation for looking at the first derivative of a function f(x). So we're going to set f(x) as e to the power x and put that into this equation here. We're going to apply the rule that if a to the power m times a to the power n is am plus n, and we're going to expand it out like this. We're going to pull e to the x out of the brackets and evaluate it separately like this. Since there's no h component in e to the x, as h approaches 0 it has no effect. However, we'll go to our GDC to see what happens to e to the h minus 1 over h as h approaches 0. We're going to use the spreadsheet function on our GDCs. On one side we're going to type in loads of numbers which are gradually getting smaller and smaller and approaching 0. Once we've done this, we need to enter in the formula e to the power h minus 1 over h, and we're going to do that by selecting the variable h to be the boxes in column A. We'll change the number of decimal places so that we can see up to 12 decimal places, and you can see that up to 12 decimal places this clearly has a tendency to go towards 1. So we can say that if f(x) equals e to the power x, then the derivative is also e to the power x. We'll put it in a blue box because it's important. Okay, so let's look at the graph of ln x and its derivative. You see that the derivative takes the shape of the graph 1 over x. So let's have a look at the table function, and we'll see more clearly that the graph is indeed 1 over x. When x is 1, the derivative is 1. When x is 2, the derivative is a half. When x is 4, the derivative is a quarter, etc. Okay, so we do the same thing we did with e to the power x, and we'll analyze it by the first order differential using this formula. And we're going to say that log m minus log n is log m over n, and we're going to simplify it like that. The next stage we're going to make in simplifying this is we're going to say that 1 is equal to x over x, which is 1 over x multiplied by x. Okay, and it'll become apparent why we've done that in a moment. So we're going to pull out the factor of 1 to the x because there's no h's in it, and h approaching 0 doesn't have any effect. And we end up with x over h times log of 1 plus h over x. We're going to apply another log rule here. K log m is equal to log m to the power k. And we're going to use that to pull this x over h up to the top of the part of the function inside the logarithm. You might have realised that 1 plus h over x to the power x over h looks a little bit like 1 plus 1 over n to the power n. And you might also have remembered that the limit as n approaches infinity of 1 plus 1 over n to the power n is the number e. What we're going to do now is we're going to say that n is equal to x over h. And as h goes to 0, x over h, which equals n, tends to infinity. Also, we're going to say that 1 over n is equal to h over x, which is implied if n equals x over h. Let's go back to our original working then and throw in these new things. So we've still got the 1 over x, only now we're looking at the limit as n approaches infinity of the log of 1 plus 1 over n to the power n. And that is the natural log of e, which is 1. So we're looking at 1 over x multiplied by 1 equals 1 over x. So we can say that if f of x equals ln x, then the derivative is 1 over x, and being important, it goes into a blue box. Right, and that's the end of the input part of the lesson. There's a couple of worked examples to go through. Remember, pause at the start, try and work through it. If you get stuck, then press play and look at the rest of the video. I'm not going to talk you through the work examples because I'm tired of talking and you're probably tired of listening to me. So you can enjoy some music. See you next time.